This mic is working okay? I'm going to sometimes ask questions of you guys, make it a little bit interactive. Otherwise, I could have just stayed in New York and posted a YouTube video, right? So, you know, it'll be fun. So, yeah, whole bunch of metrics, calibration, discrimination. Do we have any machine learning people here? Yeah, it's the lift gain, precision recall, F1. These are all things that the machine learning people like. Actually, the last talk I gave, one of the last talks I gave was on AI, and I started it with a picture of somebody with a wheel, and it said a real life picture of an AI scientist reinventing the wheel. And I retweeted that this morning because apparently a big paper came out on AI which says don't dichotomize your variables before putting them in the AI model. This is a big finding in AI, which we of course known about in statistics for decades. So yeah, what should you use instead of these other models? So just a general point, I know we're talking a lot about prediction. And I just want to be clear that what I understand prediction to mean is there's some information I have and some information I don't have. And I just want to use the information I do have to say something about the information I don't have. So that would include diagnosis, right? I've got the palpation of the body. I know how your body feels. I don't know whether you're wrong, right? Prognosis, what's going to happen in the future. In cancer, sometimes we make this distinction between prognosis and prediction, and prediction is what happened in treatment, and prognosis is what happened after treatment. Moving that aside, whether it's AI, ML, a blood marker, a binary diagnostic test, conventional logistic model, tea leaves, it doesn't matter, right? The way of thinking about it is whenever we do any of this type of work, we essentially have two columns of data, and one says what happens to the patient 0, or in the simplest case, a 0 or 1, and the other one what we think is going to happen to the patient, so it's a probability. So when you have a data set like that, you can calculate one statistic, a sensitivity, a specificity, a ROC curve. There's something else. On the one hand, I gave a talk at the University of Copenhagen about this. Apparently, after I left the faculty meeting, they were like, why are you inviting people who hate statistics to the statistics department? But this idea that I was somehow kind of anti-statistics, and so I don't actually hate AUC, and like just to prove it, this is a paper I'm working on. Look, it's got my name there, Andrew Vickers. It has the word statistical predictions, and it has AUC, and here's a calibration plot. I do actually use and like these things. I just think they have some limitations, and they're for some purposes and not for others. Okay, so this is Mike Gatan, and some of you may know that Mike Gatan has really led the charge on prediction modeling in cancer. And he has actually an interesting story that he tells, which was that he was at University of somewhere in the South, looking at predicting in the Department of Economics or whatever, trying to predict bankruptcy. Could you predict whether a company would fail? When he was diagnosed with lymphoma, and he goes and they say, he says, well, what are my chances, doc? And I said, here, take this brochure. And he read his stage 4, and he read his chances of survival were 5%. He's 24 or something. This is like a traumatic. He goes traumatized. He goes back to the doctor like, oh no, I wouldn't worry about that. You're only technically stage 4. You're really more like stage 2 because the tumor is stage. He was like, why are we not giving better predictions to cancer patients? So he actually has done a lot of work and really led the field with thinking about cancer as a prediction problem. We had a meeting at the Cleveland Clinic where he's the chair a couple of years ago. And this is what he laid out as the challenge with the conference. So a clinician comes to you, there's 2 models or tests or whatever, and wants to know which one to use. Which statistical method do you use? So let's try that problem. Okay, so here's the scenario. So men aged over 50 will get a PSA test, which is, and if you have a high PSA, that's suggestive that you might have prostate cancer. or at least, prostate cancer you want to treat. But the problem is that most men with a high PSA either have no prostate cancer or the sort of low-grade prostate cancer you'd rather not find. So there's this idea that maybe what we should do, instead of just biopsying every man with a PSA, we can use a statistical model to predict who has, depending on their age and their clinical symptoms and all this kind of stuff, try to predict who actually has aggressive prostate cancer. And so we've got these two models, model A and model B. I'm presenting all the statistics that I was taught when I first learned statistics to evaluate models. So we've got, this is the calibration plot. Here's the AUC, the R squared, root mean squared error, the Brier score. Has anyone heard of the variance of p hat as a metric? I'm glad. I've never ever heard of this, but I sent this to Frank Harrell. I said, well, God, I've got to put the variance of p hat in there, otherwise, no one can tell.
On the survey research world.
Is it? Oh, okay. Well, that's interesting. But I'm like, what are you talking about? I've never even heard of this. Well, anyway, for those, you can look at the variance of p hat. Everyone else can ignore it. Here are all the if anyone's interested in machine, does anyone know if this is a precision recall curve? Does this make any sense to you? The machine learning. I have no idea, but you actually see these in the literature now, these precision recall curves. But let's just stick to this one for now. So should we use either of these models? Which model should we use? Any thoughts or comments? So my first bit of feedback is I'm seeing a lot of very blank faces, a lot of expressions like this, right? Which is a little bit odd, right? I mean, this is the most basic thing we want out of any metric to evaluate a prediction model, is to tell you whether the prediction model is any good or which of two prediction models is better. And I've given you all the metrics that we're taught, you guys teach, and that we see in the literature. And I'm asking the most basic question, which model is better? And I'm like, oh, I'm a bit confused, right? I can't really tell. Does anyone want to say it's, you're probably gonna say, well, in my judgment, it's A because of this, that, and any thoughts on that? Anyone wanna go on?
So I like A because it's doing better job at higher predicted values.
Up here.
Higher predicted.
So it's got a higher AUC. Yeah.
What I mean is that when the predict probability is higher, the actual.
Oh, I see, right. So you're worried about this miscalibration here.
Right, at the high end,
Yeah.
at the right side.
Yeah, it's interesting because most people are actually more worried about this miscalibration. So a lot of people would say, if you have a 50 or, this here, if I tell you you've got a 50% risk of cancer and it's actually 70%, it doesn't matter. You're going to get a biopsy anyway, right? So, and it's interesting that you say that. Just out of interest, a lot of people say we prefer this model. We prefer. That worries you, but other people say, well, that worries me. I'd rather, if I've got I don't like the idea of telling someone they're 10% and it's actually a 20%. But anyway, that's just an interesting thing. Anyone else got any thoughts? So you prefer model B because of this. Else want to take a shot at it? I mean, this is kind of bad, right? You've got a bunch of really experienced statisticians and you can't, interpret the most. A lot of people like A because it's got a higher AUC, by the way. A lot of people tell me B because it's not miscalibrated. I'm like, well, how much better is the calibration here than here? I'm like, well, you can kind of. All right, well, here's another example. So let's imagine that this has now become the standard model, right? We've adopted this model. We've decided that this is how you should be deciding who gets a biopsy. And this group of researchers come along and say, well, we can make this a lot better. The way that they can make this a lot better to predict prostate cancer is to take prostate volume. The reason why you might have a PSA is either because you've got cancer or you have a benign enlargement of the prostate gland. So if you just measure the volume of the prostate glands, then you've got a good idea whether there's a benign enlargement and therefore not cancer. The problem is that you have to come into the hospital and get an ultrasound probe put up your back passage, which guys don't want to do, right? It's an expensive and uncomfortable test. Any thoughts? So this is, well, first of all, let's just assume that it wasn't an uncomfortable test. This is just, a standard model and a new model. Which model do you think we should choose between those two? I mean, I think it's a pretty easy question. You want to? No, this one, right? I mean, the AUC is way better. The Brier score is way better. Then it's, you know, if anything, the calibration is better. Some statistician tried to explain to me why this one was better to do with the partial ROC cut. I had no clue what they were talking about. I think there's no question that this one is better than that one. Right? I'm not trying to trick you there. But the question is, so you said this one on the right is better. The question is it worth going through a transrectal ultrasound, bringing a man in, putting a that passage? Is the improvement in value worth this test?
Standard model, and if it looks bad, do the uncomfortable.
You mean
Sequentially.
Oh, you could do it sequentially. Well, right, but then okay, but we could do that, but then we would you could actually create a new model, which is the sequential, right? And then we would have the similar sort of problem. So I mean, yeah, or yeah, use a totally try and get a different biomarker. I mean, you know, I understand that, but let's just stick to this. That these are our choices. Is it worth it? I don't think you can tell. I don't think you can say, is an AUC improvement of about 5 points worth an uncomfortable test, right? Because an uncomfortable test isn't in the units of AUC.
Can we ask the patient?
What is it improvement?
No, I mean, like,
Yeah, you can ask the patient.
is a better calibrated test, which is probably going to be more
really? You want to explain calibration discrimination to a patient?
I mean, you can.
Brier score.
Accuracy.
You could say, yeah, but so how much more accurate is it? And you're like, well, the mean square error goes down by. I don't think you can't actually really put it in patient terms. I mean, I take your point. I just don't think that these are our metrics. We're going to say, is the uncomfortable test worth 0.05 on your AUC, or a decrease in the CDR square, or increase in the CDR square to 0.5, 0.8?
Some patient, it's not uncomfortable.
It's really, believe me, it's no one wants this. All right, well, let's make it a really easy one, because this is what we typically see in the literature, right? I've got a model, it's pretty well, and let's assume this is on external validation, by the way. It's well calibrated on external calibration. On external validation, it's pretty well calibrated. AUC is pretty good. Do we think we should use this model? So in this scenario, so patients with cancer, you often want to take out the organ, like prostate or the bladder, and then also the lymph nodes surrounding it, because, you know, if cancer can spread to the lymph nodes. But if there are no cancer on the lymph nodes, you don't want to take them out, because that can cause side effects. Like in women, they end up swollen arms. So in this model, you would say, well, hang on, let's see what your risk, you know, if you're at high risk of having lymph nodes, you take them out. If not, you won't. So here's a model, and it's pretty good AUC, pretty well calibrated. Should we use this model to determine who gets a lymph node dissection or not? I mean, this isn't what we normally see in the literature, and would you at least accept that most people say, this is a good model, use my model, yeah? I mean, anyone got any thoughts on this? Does anyone agree with them or disagree?
So you're not thinking of the consequences after the fact here, right? If you took, is it much better benefit if you actually do take them?
Okay, because that's you're coming on to the rest of the talk. So yeah, but you're saying it depends on the consequences, and we'll actually. This is, I mean, we could go on and on. This is just to give you another example. This is a standard model, and then another model which is a lot better. This is for so this is in patients who with cancer, and they have bone metastasis, and it's very painful. But you can get this orthopedic surgery to kind of correct it, and actually reduces the pain a lot. But you're not going to put anyone through this unless they're going to survive a reasonable period of time. So if someone's at a high risk of death, you're not going to give them the surgery. That's the model. And so you've got this model that isn't very good, and someone comes along with a new model, and it's got these blood markers in, and the AUC goes up enormously, but on external validation, it's miscalibrated. And so the question is this amount of miscalibration worth this improvement in AUC? And people vary. I mean, just in the interest of time, I'll keep on ticking along, but people vary. Frank Harrell would say never use this model because it's miscalibrated. And I say, well, what counts as miscalibration? And he says, well, that's a judgment call. And that's what we're kind of left with, judgments about whether something's, which is not really what we want. I'm just showing you this because this is a very slightly different version, different models that have just very fractional differences in miscalibration. Let's bring it down to now binary test, right? This comes back to Jeremy's point about consequences. But so the first time I ever gave this is again going back to the prostate cancer example. Well, imagine instead of a model, we have these binary markers, right? So if you've got a high PSA, great. Should you take a pre-PSA test or eventually 2 tests? And this is the sensitivity, specificity, all the things I was taught, back in college to report for a binary test, the blah blah blah, right? So the first time I ever gave it, this was all of the department chairs of the major comprehensive cancer centers, like the NCI, they're all sitting in the table around, and I said, which test should I use? Can anyone either guess what they said or want to comment on which test should we use? Go on.
So, well, this is a case where there is going to be, is this a case where there's going to be additional testing if this is found positive?
Yeah, well, the point is we want to make a decision about whether to biopsy the man.
Yeah.
Right.
Yeah.
So that is the decision we're trying to make. There's no additional testing. We're going to use these markers to make a decision about whether to biopsy. We're going to use these markers, and if we're going to use them, we're going to use one or the other. On the basis that if that marker is positive, we're going to biopsy the man, and if it's not, we're not going to biopsy.
Yeah. So in this case, where there's a relatively low harm compared to say a prostatectomy later in the process, I would prefer something that's more slanted towards positive predictor values than negative predictor values.
Right. So it's kind of about sensitive. So you're saying specificity is more important.
Yeah.
Okay. Well, I think the most general, that's interesting, most general answer, this is the one given by the head department chairs, was it depends on whether specificity or sensitivity is more important. It depends. And so the obvious response is, well, how does it depend? Right? This is it's quite obviously they're not the same. And in this case, this is a false negative. This is a biopsy, which is very uncomfortable and painful and could cause sepsis. It's a hell of a lot better than dying of metastatic prostate cancer. And this is actually generally true in medicine. It's interesting, the AUC assumes that sensitivity and specificity are equally important, and I can't think of a single case where that's actually true. Maybe someone come up with something. The point is that this is statistics. What we do is we come up with a parameter and we come up with a formula and we apply the formula to the parameter and we come up with an answer, right? And at the moment, what we're doing is we say, well, it depends on sensitivity and I'm worried about the calibration at the high end. And I said, someone else is worried about the calibration at the low end. Okay. So this is my conclusion, is that the statistical techniques do not incorporate these clinical consequences, which is what you were saying. And so they cannot guide the clinician. And that AUC, Brier score, F1, calibration are actually not for the clinician. They're for us, right? They're to help us build better models. If I build a model that's miscalibrated, I want to find out why. If the discrimination is poor, I'm going to talk to the investigators and say we need some better markers, better predictors. So there is actually a dependence parameter, right? It depends on whether sensitivity is you said you're interested more in specificity.
Oh, sorry, I meant sensitivity.
You did. Oh, well, that's another example. You thought sensitivity is more important. Yeah. Well, anyway, the dependence parameter, as it turns out, is not sensitivity or specificity. It turns out, and I can explain this later, that it is impossible, and you often see this here, we fix sensitivity at 90%, see how specificity varied. It is impossible to actually choose a rational value of sensitivity or specificity, because the problem solved by sensitivity is, doctor, there are 2 men outside the door that have there's a guy outside the door that has the disease. Oh, let me guess the probability his test came up positive, right? It's just like something that never happens, right? So what is this dependence parameter? It's called the predicted probability of the disease. And how it is defined is that this threshold probability of disease, rather. And the threshold, it's defined as if your predicted probability of disease is greater or equal to your threshold probability, you're going to accept some kind of intervention, right? Whether it's the prostate biopsy, or it's delaying surgery or taking out lymph nodes or whatever it is. So let's sort of think through this. Should I explain? Does anyone know? I actually asked some students before that haven't been taught anything decision analytic. Do you want me to explain this, how a decision tree works? Should we go through this? Okay, so it's actually a complaint I've made is that a lot of what we're doing in statistics is about making decisions, and yet we don't teach statisticians decision theory at all. And I was like the only person that ever went to the ENAR and the Society of Medical Decision Making conference, and they were always on separate coasts, like in case like anyone met at the airport or something like that. But this is a decision tree. So let's just imagine I'm like, hey, let's bet. They're like, what's the bet? I'm like, well, we're betting a game where we're just rolling a dice, and if it's a high score, you get $1, and if it's a low score, I get $5, right? We're playing this game quite happily. I'm like, I've got a much better idea. You're going to roll the die. If it's a 1, you give me $2. Sorry, you get $2. If it's 2, 4, 5, or 6, you lose $10. If it's a 3, you roll again. If it's a 2 or a 4, you're going to get $100. If it's 1, 3, 5, or 6, you're going to get $5. Do you take the bet? Right. So this is how you break it down. You say, well, I've got a choice. And so this square means a choice. And here are all the options I have. I take the new bet or I take the old bet. I guess you could say stop playing, right, as well. But so if I take the old bet, then this circle means all the possible things that could happen. And basically I either win or lose. And here's the probability and here's the outcome. And then if the new bet, here's all the different possibilities. And for each one of these different things that could happen, and they sometimes branch, if this happens, then either that or that. And you can either, you win or you lose, and you have a probability of each. And to solve it, what you do is just expected utility. You multiply the probability by the outcome, and you sum up everything for this decision. You sum up everything for that decision. And so you can actually sort of work it all out, and your expected winnings, we know what it is. It's easy on the old bet, your expected winnings is 0. Right? On the new bet, the expected winnings is minus 22 cents. So you don't take that bet. And we do this thing in medical decision making. You take the old drug or the new drug. And with the new drug, you're either cured or not cured, and it has a side effect. Whereas the old drug, you're either cured or you're not cured. And then you put in the probabilities and then the outcomes, and all that comes from the literature. And then you can actually work out which gives you the best expected outcome. So let's look at a decision tree. Let's imagine that you have to choose whether to have a treatment or not. And you don't know whether you have the disease. So this is the decision tree. Either treat or no treat. You either have disease or not. And of course, this is the probability you have disease, which is the same whether you decide to have treatment or not. It's the prevalence of disease part. And then these things on the end is what we use in medical decision making. It's not like a bet where you have money. It's what we call utilities. And the utility is from 0 to 1. And 1 is perfect health and 0 is dead. It's normally how it's explained. And so this is the utility of a true positive. And here's the utility of a false positive, so false negative, true negative. So the problem that we have here is that these are very, very difficult to specify. So when you go to the Society of Medical Decision Making, you'll see something like this. And then they will talk for 20 minutes about how they managed to get these values. Because if you take prostate biopsy, this is like, what's the harm of getting a biopsy when you don't need one? Well, we looked at the risk of sepsis, and then we put a utility on that, and then we looked at pain and time off work. And then this one would be, what's the probability, what's the harm of not getting a biopsy when you do actually have prostate cancer? Well, we looked at the probability of progression to the next day. It gets very complicated. So this is the problem with decision analysis. These 4 utilities are incredibly difficult to specify. But there's something else you can do. Remember, we've got this idea of the threshold probability. And let's imagine that the disease prevalence is the threshold probability. So what do we know? So we've got this decision tree, but now we know that the expected utility up here is equal to the expected utility there. Because if I say, your risk of disease, at what risk of disease would you get a treatment? You say 20%. You're like, oh, that's your risk. You're like, now I'm not sure what to do. Right? So you know that this is the same as that. And so you can, you just do a little bit of math and you can move it around a little bit and you get this. So this is basically saying that the harm of a true positive compared to a false negative over the harm of a true false negative compared to a true positive is the odds of the threshold probability. This is a very, very well-known and intuitive finding. So let's just imagine this is the what's the probability of rain at which I'm going to make this decision? Right now, the two decisions are: is I'm having a wedding, and I want to make sure do I put up stuff to make sure it's waterproof, right? And then the other one, if it's going to rain, I'm going to waterproof my tent. And here, I'm going to go on a hike, and if it's going to rain, I'm going to cancel the hike. Now, what probability of rain, assuming it's not insanely expensive, at what probability of rain would you waterproof the tent? Anyone want to say? It's going to be 90%, it's going to be 5% or 10%. What would anyone think? Is it going to be low or high? Well, it's going to be low, right? It's going to be low. Why is it going to be low? Go back to this equation, right? It's going to be low, and it's because look at these different harms. What's the harms, right? If it rains, the false negative is very harmful here, right? If I don't waterproof the tent and it does indeed rain, then I've ruined everyone. I've ruined, everyone's big day, and everyone has a lousy time. 100 people have a lousy time, especially the bride and groom. Whereas if it's a false positive, then okay, I've spent a bit of money. How about going for a walk? Would you think that canceling a hike for a walk? What probability would you cancel the hike? I think low, high, intermediate. What risk of would you cancel your hike? I think medium. About medium, yeah. Probably 40, 50, 60%, right? Because, yeah, it's annoying having to hike in the rain, but it's not the worst thing in the world, right? And, if we don't go on the hike and we're sitting around getting bored at home, right? So it's actually the cost of a false negative and the cost of a false positive are about the same, right? So this is just a very, very intuitive idea, is that the threshold at which you do something is informative about the relative harms of a false positive compared to a false negative. So now we can get into a little bit more and look at the actual utility, the expected utility, right? So this was the utility of a true positive. So what's the expected utility is the probability of a true positive multiplied by the utility. Right? And so if we've got the utility of a test, you just add them all up, right? The utility of the test is the expected utility of the true positive and false positive and so on and so forth. And you can kind of sort of rearrange that to get this. And then you can say, well, what's the utility of doing nothing? Which is that. And now you can say, let's subtract one from the other and say, what is the utility of a test compared to doing nothing? Let's define this as 0. And you do a little bit of rearranging, and you get this relationship, right? And what we're going to define this one is the value of doing a test compared to doing nothing. And a test could be a prediction model or whatever. This is the units of true positives, right? The value of a true positive. So the value of a test in the units of true positives is this here. I'm going to explain, but that's called net benefit. So what is this thing here? What's this? Probability if test is 1, if disease is 1, probability of the true test. What's that called? Sensitivity. What's this? Probability D of disease. Prevalence. What's that? Is there a probability of treatment of your
Specificity.
or minus specificity? Right? His lectures are really great, by the way. This fan. Yeah. That's 1 minus. This is 1 minus prevalence. Oh, and this one here, this is this complicated 4 difficult to specify parameters, but we already know that it's this odds at the threshold probability. And so this is the definition of net benefit, and we can actually clinical net benefit. So this is the definition. We can actually derive it a bit from the AUC. This is an AUC, and we're going to say, well, let's weight it somehow by prevalence, because it's going to be more important to find a common disease than uncommon disease, and then just weight it by its consequences, which was what Jeremy was saying. It depends what happens if you take out the lymph nodes or whatever, and that's how you end up with net benefit. So the nice thing about net benefit is it has a clinically interpretable unit, which is it's the number of true positives per patient if the false positive rate was 0. Let's give some examples of that. So remember this, like sensitivity. Do we use the free PSA or the HK2, or I was looking a bit blank, and someone said, well, it depends on I like this one because of the specificity. Actually, I meant sensitivity, right? Everyone gets very confused. Well, with net benefit, we've got the sensitivity and specificity and the prevalence. We just multiply them together and we get the net benefit. And we have an answer. We use the free PSA test, percent free PSA, because that has the highest net benefit. It's done. No, like, well, I kind of prefer this, and my judge, I tend to not like miscalibrated, right? Unequivocally, we've got a parameter, we have a formula, we have an answer to our question. So one of the problems, of course, is that we've chosen this threshold probability of 20%, and that might vary, right? Somebody might be really worried about cancer. One might be an old guy who's like, do I really have to go through this doc? A friend of mine had a really bad experience with the biopsy. So you can actually vary this threshold probability. Now I'm doing this for didactic purposes, right? It's not to actually do it quite in this way. But this is your threshold probability, and this is your net benefit. You're just plotting one. So as you change the threshold probability, you're changing this multiplication factor there. And what you can see makes perfect sense here. If your threshold probability is very low, and you're going to say, look, whatever my chance of cancer, even if it's a really low chance of cancer, I want the biopsy. I'm terrified of cancer. Biopsy everybody. Makes sense, right? No test is going to give you enough confidence that you're negative, right? If in between, free PSA was more sensitive. So if you're kind of more worried about cancer, you're going to have a more sensitive test. If you're a bit more worried about an unnecessary biopsy, you're going to get a more specific test. Now, if you're the sort of person that's like, there's no way I'm going through that biopsy, it sounds terrible unless I've got a very, very high risk of cancer. You're like, well, just don't get biopsies because no test is going to kind of give you that level of confidence. So it sort of makes intuitive sense. And then we can actually come, and again, this is just for sort of didactic purposes, we can say, if you have a threshold probability, between about 5% and 25%, if it's less than 5%, you'll biopsy everybody. Here it's biopsy according to your free PSA. Here use HK2, and above this don't biopsy anybody. Turns out all of this accords very well with standard biostatistical theory. So for example, this is the treat all crosses at the prevalence. Right? So if someone's threshold, if you're just going to treat everybody, you're saying your risk is the prevalence. And if your threshold probability is the prevalence, then the net benefit of doing that compared to doing nothing is 0. You're indifferent between the two. Think about it in terms of positive predictive value, right? For a binary test, what's my risk after a positive test? If I tell you that, and that is your threshold probability, then you're indifferent between doing the test and doing nothing. And then it turns out it crosses treat all at 1 minus the negative predictive value. So this is your 1 minus the negative predictive value is what's my probability of disease? The test came back negative. And you're like, well, that's still too high. But don't take the test, right? Just go ahead and get the biopsy. Okay. So what about a continuous endpoint? Because that was for binary endpoints. So what we have to do now is a binary endpoint is already dichotomized. But what we're going to choose our threshold probability and just define the positive test in terms of that threshold probability. So in this particular case, let's say we've got this is our PSA example, and we've got this model, we're going to use this threshold of 20%. So this is the net benefit if you're biopsying all men with a elevated PSA, right? Do a biopsy everybody. So this is what we're going to say. So what proportion of men, we're going to call you a positive, your threshold probability is 20%, right? So we're going to biopsy you if your risk is 20% or higher. And it turns out that you end up doing, you do about 500 biopsies rather than 1,000. And you find, you know, a good proportion of the cancers, 211. And then you just you've got your net benefit here, and you end up, oh yeah, this model has higher net benefit than our standard procedure of biopsying everybody. This is a simple clinical interpretation. It's in true positive. So it's a bit like saying, imagine that we had some strategy in which for every 100 patients, we did 14 biopsies and all of them had cancer. Right? We did no unnecessary biopsies. Our strategy is equivalent to that. The other thing you can do is you can say, well, you know, what's the difference between the model and treat all, and just do a little math, and then you can say, okay, using this marker is the equivalent of doing 19 fewer unnecessary biopsies and missing no cancers. Now, of course, we do fewer biopsies and we miss some cancers, but this is the equivalent. So this is the full decision curve analysis, is then to say, oh, well, people's vary, right? So we're going to vary this threshold over appropriate range. Let's go back to our problems, right? Well, I don't know. I prefer calibration to high end. Let's look at it. Okay, so let's first of all think about the threshold probability here. This is for aggressive cancer. And so, no, you know, I don't know any urologist who would biopsy somebody if they had a risk of aggressive cancer of less than 5%. Because, you know, you can probably do a biopsy the next year and still find the cancer in it. On the other hand, I don't know anyone who's got a risk of greater than 20% of having aggressive prostate cancer. Like, nah, it's not high enough. I don't need a biopsy. So we're going to look at this range between 5 and 20%. And what we see is that model B is best over the entire range. It has the highest benefit. So we have an answer. Which model is better? Which model do we use? We use model B. Done. No judgment. This was the lymph node dissection, and you said depends on the consequences. This is the decision curve. So what's happening here is, as you can see from here, that these are the deciles. So the average risk is whatever it is, about 30%. But look at the threshold probabilities. If you leave in a cancerous node, the patient will have a recurrence and likely die. Right? If you do do a lymph node dissection and the patient doesn't need it, they may get some side effects. So it's way, way worse to leave in leave in a lymph node than to do an unnecessary lymph node dissection. So our threshold probabilities are really low. They're down here. And what we've seen is that the average prevalence is 30%, and the model just can't push enough risks down low enough to make any difference to that. So this looks great. When you do the decision curve, you see nothing. This is how you can incorporate sort of test harm, right? This was the uncomfortable test. So that benefit is basically means you're putting things all on the same scale, and that scale is false positive. So sometimes explain this. If you we wrote a sort of didactic paper on this in the British Medical Journal. We say, think about net benefit as profit in business. Imagine that I go to Europe and I buy wine for 100,000 euros. And I sell it in the US for $130,000. How much profit have I made? Well, my income is $130,000. My cost is 100,000 euros. I have to multiply the cost by an exchange rate to work out my profit. That's all we're doing. Well, we're just adding this. Well, there was also the cost of import taxes or whatever. We're just adding something more in the same unit. Now, of course, this is this is the standard decision curve, and you can see the standard model plus the invasive test is way better, right? It's got a higher net benefit across the entire range. So that deals with that. That accords with our intuition that this is a better model than that. But this is how do you incorporate the harm of the test? How do you put it on the same unit. Well, what you do is you say to the doctor, imagine this test was perfect, right? That doing this transrectal ultrasound would tell you invariably who had cancer and who didn't. How many patients would you give the test to in order to find one cancer? So I think we assume, what is it? I think 0.2. What do we do? Here we say I'd do it to 40 patients, right? I mean, I'm not going to bring in more than 40 patients and put them through this procedure in order to find one cancer. So we've now put the harm of the test in the unit of true positives. And so all we have to do is subtract. This is the net benefit. And we're just going to subtract the test harm. And this is what we get. We can see the standard model plus the invasive test actually has lower, it's a better model. Taking into account the fact that you actually have to come in and do something that's costly and uncomfortable, it's not worth doing. And it's actually worse than the standard model, and in many places worse than just giving everyone a biopsy automatically. This was the risk of death for candidates for palliative orthopedic surgery. This is the decision curve. Turns out the one with the blood markers, this actually can tell you that, yeah, there was miscalibration, but the improvements in discrimination offset the problems with calibration. Again, got to think through the threshold probability. At what probability of death would you withhold surgery? Of early death would you withhold surgery? And it's much higher than like lymph node dissection, you know, because and it varies quite a lot because it depends how much pain you're in. You know, you can imagine that if a patient is in really desperate pain, they'd take a 50 or 60% chance of early death in order to have the surgery. And others will, like, you know, the pain's bad. They really want to have a pretty good guarantee that they're going to live for a decent time. This was to show that I can't visually tell the difference between these two plots, but in this other case, the miscalibration, it doesn't look much worse here than there, but the miscalibration is such that it ends up being, this standard model ends up being kind of worse across an important part. Just let's see how we're doing for time. Grab a little break. Yeah. So the decision curve analysis was developed in 2006, and since that time, there's been a lot of subsequent research. So one of the findings is, does anyone remember the net reclassification improvement or index? Remember this? This came out about this was like a big statistical flash in the pan. Is that they came out with this new way of testing whether a model was any good, and everyone started using it. Had like 3,000 citations within 2 years, and then it turned out that what this model would always give you a low p-value. It was like highly anti-conservative, which is, by the way, a good piece of career advice. If you ever want anyone to use your test, just make it anti-conservative, because the clinicians will absolutely love you. Because, you know, they're like, oh, doctor, it looks like my biomarker is useless. Here, use the NRI. Wow, amazing. My marker's amazing. And yeah, so anyway, this went down. But while they were doing this with the Margaret Pepe, who you might know, and Thomas Gertz, they actually evaluated a whole bunch of different tests, and net benefit. The key characteristics of what's called a proper scoring rule. And that benefit does meet the criteria for being a proper scoring rule. This is that you know, time to event data, competing risk, you can correct for overfit, all the normal things. In this paper, we actually told you how to do 95% confidence intervals. Turns out this is generally a bad idea. And we subsequently published on why you don't need confidence intervals for decision curve in general. We could actually, so if your model is not to predict the risk of something, but the change in risk, like how much does your risk of death go down if you take adjuvant chemotherapy or whatever? The formula changes a little bit, but we published on what that formula is, and it's this is again, it's just this idea of a net benefit is income minus expenditure times an exchange rate. So the income is the number of events you avoid if you take the drug. The expenditure is, you know, how many patients you're treating with this drug, and then the exchange rate, you have to specify this in your trial, right? The difference. It's a very simple formula there. And this is just an example of the way you would do that kind of math. It's like, okay, we can treat all, we can treat with the drug, we can treat none with the drug, or we can treat patients if they're high risk from the model. And we can work out the number of events avoided, number of treatments given, and then work out the net benefit. In this particular case, net benefit is slightly higher if you use the model than if you treat all, and that would justify the use of the model to select patients for treatment. This is a recent paper with some machine learning folks. The big problem in machine learning, and does anyone read a lot of machine learning literature? Does anyone? No? Okay. What you'll notice is they never talk about calibration, which to me is the most, I don't really care about discrimination, right? That's like, is my risk going to be higher than someone? I care about if you're giving me a risk, that it is the correct risk, right? And they never talk about calibration. That is because the history of machine learning was all about resource constraints. It was all under resource constraints. It's like, which 5 products on Amazon are we going to show you, right? Or which of the patients we're going to send to the ICU, or which ORs are we going to open up and send patients? It's all about rank ordering, which is why they've traditionally not cared about calibration and why it's caused the problems, because now they're moving into areas where calibration is important. But anyway, in this situation with resource constraints, so for example, this is a model to predict whether you need to go to ICU. There's a very straightforward way of assessing that benefit under resource constraint. Also, it's a very widely used, this was, so 1,600 papers in 2022 actually had the word decision curve analysis in the title or abstract, right? So obviously a hell of a lot more papers use it than actually have it in the abstract. I used to follow the citations, but now most people aren't actually citing. They're just saying we use decision curve analysis, right? And, you know, I hope no one cites Kaplan and Brier when they do a survival study. Similar sort of thing. Just some examples of it being used in the literature. And I like this is one of the first times that they showed this. This were 2 risk calculators in prostate cancer. And they showed that one is better calibrated. So this one's better calibrated, this one has a higher AUC. And you show you shouldn't use either of them. Right? Is that they're only better than just biopsying everybody at a threshold probability of like 30% or more, which is ridiculous. No one's going to say, oh, 30% risk of cancer, forget it. I'm not getting biopsy, right? So this is the kind of range we're interested in. This was the first publication in the British Medical Journal. This is Framingham. And the interesting one is that in the UK, there's something called NICE, is the National Institute for Clinical Evidence. They developed their own Framingham equation, which is for the prediction of cardiovascular events. And I thought this looked pretty good, right? Good AUC and pretty good calibration. But this is the decision curve. And you'll note the threshold of 20, everyone knows this is the common threshold in the UK is 20%, right? So if you have a threshold of 20, around 20 or 15, 20%, you can put on statins or blood pressure medication. And you can see that the framing equation NICE framing equation had no benefit whatsoever in this range. Their new equations, what they call the Q risk did, so they recommend the Q risk. But it's just interesting is that we think, oh look, that looks pretty good. And it turns out it's absolutely no benefit. Do want to point out, it's been recommended, this is an editorial of the Annals of Internal Medicine, this is JAMA, this is Journal of Clinical Oncology, this is just a recent series in the British Medical Journal, how do you evaluate clinical prediction models. All of these are recommending decision curve analysis. Again, if you're in machine learning on the website, which I'll show you, there's endless papers on machine learning guidelines saying use decision curve analysis. Just interested in time before I'll actually just sort of jump through that bit. Decisioncurveanalysis.org is a website where you can download software. There's a very easy software tutorial that will say, put in this code and you get this. Well, that's not very helpful because you actually, you've got to put in this different option to make the graph appropriately sized and so on. And it has a whole bunch of, it has a bibliography with links to the paper, introductory papers, discussion papers, methodology papers. So yeah, I guess we can come to this sort of conclusion slide. And again, I would recommend, if you're interested, going to this decision curve analysis website. The common metrics that we use, like calibration, mean square error, Brier score, AUC, which I use all the time in my work, they're for us as analysts to help us build better models. They do not tell us about the clinical value of the model, which is what the clinician, the patient, the decision maker wants to know. But decision curve analysis does. What you need, you don't actually need much additional data to do this, right? All you need to do is have a conversation with the clinicians. Right? It's not, you don't have to run around and work out what the risk of prostate cancer progressing if you don't need that. And the interesting thing, they've said, well, what if they, a lot of people, here's a decision curve. Let's go down here. I've heard people say, it's like, what if you don't know what the threshold probability is? You can't do a decision curve. And I say, if you don't know what the threshold probability is, you can't use the model anyway, right? Because the model comes out and says it's 30%. Like, well, I don't know if that's high or low, right? So, I mean, so you have to know that. You have to have an idea of this threshold probability before you do. One of the other interesting things I have to say in practice is that when I'm working with clinicians, it's really helpful for thinking through why they're doing the model. Because they come, oh, I've got this model I want to evaluate. Like, well, what's the decision you're using to inform here? And then they think through that, like, well, what kind of threshold probability would, that actually helps people think through and make better models. It is extremely widely used. It's recommended in numerous editorials and guidelines. And finally, there's simple to use software. And that's the end of my talk. I'm very happy to take questions. Question? Yeah, go ahead.
I know you talked a little bit earlier in your presentation about how they come up with the utility of balancing the different components of that. In your experience, is there just some simple, straightforward approach to figuring out that utility and putting it to a number, or is
it about utility or threshold probability?
So the utility, so the U sub 1 and
yeah. Well, that's the whole problem with decision analysis, right? So if we were doing, anyway, let's get this slide here.
Yeah.
This is the problem, is that imagine that you actually, well, instead of the prevalences, you were putting in something else there, like positive predictive value. And you went to a decision analyst and you said, could you help me do a decision analysis to find out whether we should use this model or whatever, whether we should treat? They're like, hold on, I'll be back in 2 years. Right? Because they've got to go and look, they've got to go do all this research, finding out what the utility of this is. They look at the literature, and Jones found that the prevalence was this, but Peters found the prevalence was that. And then what they actually do is vary the utilities, because some patients think, if this was prostate cancer, some patients think erectile dysfunction is a disaster and some don't mind. It starts getting sort of very, very complicated. There's actually one funny story. I was once asked to review a decision analysis for JAMA, and it was whether a man with low-risk cancer who's 65 years old should get low-risk prostate cancer, should get surgery. Anyone know the answer to that question? They shouldn't get surgery, right? Low-risk cancer should not be treated, right? It's not even a question. So I don't know why they were doing this decision analysis. But anyway, they were talking about they used multiple hyperparameters with a conditional accelerated failure time model and a Markov model, on and on and on and on and on. Anyway, I'm reading all of these different utilities that they're using. They also have but you also have to put in these are often estimates, right? You don't know what the probability is. But I noticed that they put in the hazard ratio of 1 for treatment. And I pointed out that if treatment was ineffective, you didn't need a hyperparameter and accelerated failure Markov model to work out. So it's not I think these modeling approaches, can be valuable if they're done well. Like in this JAMA example, but they are often done well. The problem is this is really, really hard to do. And I'm pretty sure if someone comes to you, it's like, I've got a data set of a diagnostic test, and you're the consulting statistician. saying, hold on, it will take me 2 years to look up these utilities is not going to be helpful. And that's why, I mean, this is the whole point, why you turn these 4 utilities into one parameter that they have to know. And you can have a conversation with a doctor about it, right? So, you know, I've had these conversations. I just had one this morning. We were talking about lymph nodes in prostate cancer. We were like, well, you know, how much worse is it to take out lymph nodes unnecessarily compared to leaving them in? Oh, they're like, yeah, you know, it's really bad to leave them in. And so maybe probably like 20 or 30 or 40 times worse to leave them in than take them out. I'm like, okay, so we're talking about a 2 or 3 or 4% risk threshold. So you can have that conversation, and you have to have that conversation in order to advise people how to use your prediction model. Are there other questions?
It deals with, if I'm an individual, I could have a value of PT, which is my sort of concept,
Yeah.
and you could have a different one. Is that...
Yeah, so in the different ways of thinking about this, I mean, so one way of interpreting it would be you say, oh, what's your threshold? Well, so first of all, to answer your question, yes, people have different threshold probabilities, right? So if you take this, we're talking about biopsy for prostate cancer, you can imagine a young guy, who's just had 2 kids, he runs a large business. I need to know whether I have cancer. You know, it's an older guy who's got some comorbidities, who's had some bad experiences, you know, with procedures, who's like, I really don't want the biopsy. So that's why we use models, right? It's because we can individualize care, right? Instead of just saying, oh, you're at high risk, you can get the biopsy, we can say, okay, here's your risk of having cancer. Now we can have a conversation about whether that risk is high enough given your preferences and your medical state. But if your question is whether you need that before you can do your decision curve analysis, that's not how it's conventionally done. So it's not like, what's your threshold probability? Okay, now let's check. It's more that in order to justify the use of a model, you want to see that it's the best option irrespective of threshold probabilities, right? So what we're saying here, it doesn't matter what your, it doesn't matter whether you're the old guy worried about a biopsy or the young guy who's worried about cancer. Irrespective, model B will always give you the highest net benefit. So use model B in practice. So that's how it's going.
When you include like the test harm equation, is that clinician specified or is that patient specified?
Well, I mean, it's, you know, how do you get these numbers? I mean, you know, I think normally in practice it's done with patients. I presume you can do it with patients. You can also use different values and see what comes up. But the point is that it's kind of straightforward to do, and it's in a way that we can easily understand and talk about. It's in a unit we can understand. Normally, we don't actually involve patients because we have ranges. And we're not saying, what is your preference? We're like, let's get an idea of what's a rational, what's, you know, outside this range. We're not going to specify what the true probability is, right? And that's going to vary between patients. But let's specify what it would be irrational to do, right? So if any patient said, I need a 40 or 50% risk of cancer before I'm going to biopsy, you're like, okay, let me explain to you. I need to educate you a bit more about cancer. And this, I guess the same with test harm is you could actually talk to doctors about the range, and you could, you know, use either end of the range and see if it made a difference to your findings. What I've generally found, just out of interest, is if there's any test harm at all, it's not worth doing. That's the most common situation to think about.
So in your figure with comparing model A and model B, can you go back and discuss the confidence bands on?
Oh, I see. Why we don't do confidence bands. So in decision theory, so this is now the 3rd time I've given this example today, but it's a good one. I'm in my office at work and I've got to get to an appointment. And I get a bus and I got to get 1 or 2 buses. And there are different corners, so I can't wait to see which one comes first. And there's, you know, it's the same cost, and it's not like there are any difference in coming first and getting a seat or whatever. So the only decision is which one is going to get me to my appointment on time. And so, fortunately, I have a data set. And I look at the data set and it says that the downtown bus is going to get me there on time 70% of the time. And the crosstown bus is going to get me on time 67% of the time. And there's a difference of 3%, 95% confidence interval from 10% or whatever it is, 18%, the p-value of 0.6. So which bus do you get? I mean, the point is with the decisions, you're forced into making a decision. And in decision analysis, what you do is you put all the options on the table and you see which one is going to have the best outcome. Now, my decisions are take the crosstown bus, take the downtown bus, or flip a coin. That, I think, are there any other options that are reasonable here? Can't afford a cab. I don't know. Those are my options here. So which one do I do? In decision analytic theory, you take the downtown bus, even though you're not sure it's going to get you there on time. Fastest. And so that's why in decision theory, confidence intervals and inference. There's a paper on the website you can look up. They have Steyerberg and Kauster, and we kind of explain why confidence intervals are generally unhelpful for decision curve analysis. Now, where they come in, and this is work done by Laura Weiner, sort of, as a very big prediction modeler, is that in my case of the two down buses, I'm like, okay, I'm getting the downtown bus, but I'd really like to get more data so that next time I'm making this decision, I know for sure which is the better bus to get. And so that's where it can come in with the decision curve. This can tell you, use the model, don't use the model, or whatever, but is it worth going and doing a bigger study to be sure? That's roughly what it is with confidence.
Just to pick up on that and tie back maybe a bit more to your plot there. What if I knew that the amount of, if I had data on the amount of time it takes to get there, so that 70% of the time I make my cutoff one, but it turns out that 10% of the time it takes 3 hours, and like 0% of the time it takes 3 hours on the other one.
Right, sure.
So if that model B was like had very wide intervals, model A had very narrow.
Okay. Well, right. But that's not a confidence interval. That's a distribution of times, right?
Yeah.
And with a distribution of
Couldn't you
times,
do the same thing here? I mean, wouldn't that benefit have some uncertainty in it?
in that, well, anything can have uncertainty in it because if you repeated it again, you'd get a different result, right? So let's start with your bus times. Bus times, all you do is you're changing the metric, and you'd actually then change the decision analysis. What you could say is that in your case, getting there 5 minutes early or 10 minutes early doesn't make any difference. Getting there 3 minutes early compared to 2 minutes late does make a difference. And getting there 10 minutes late compared to 5 minutes late makes a huge difference, right? And so you can actually put values on it.
I mean, it sort of becomes like a min-max, right, or something.
Right. So in that particular case, so that's decision theory in which you're weighting it. So instead of saying on time, you're saying what's my benefit.
In the end, you're right. You have to make a single decision.
But again, this whole thing is you don't. So one of the questions is like, what if it's a shit model? It's like only done on 10 patients. There must be a massive net benefit, massive confidence. Then it shouldn't be in your decision analysis because you should only be doing decision analysis on options that you're confident that you would take if it's if the decision analysis came up. So if that's somebody, when I was mentioning it, they're like, well, what if one of the buses you only had data on 10 trips? I'm like, I'd say I'm not going to consider that bus because I really don't know much about it. It's like no train types. So there, I mean, there's obviously nuances, but that's the basic. The way the decision analysis is done is consider what your options are, which may include inference. But once you've decided, okay, here are my different options, you choose the one with the best expected outcome.
It seems like you could put confidence intervals into that construction of that decision theory. You still have to make a decision.
Right. That's it. So, I mean, look, in the literature, we've actually written about this. There's all these papers showing how to do confidence intervals. But none of those papers say why or how you would, and actually wrote to someone like, what would you do?
You have to do something with that at the end, right?
And there's like this vague stuff is, a decision maker with a big decision. I'm like, well, can you give me an example? Like no one has ever shown, there's thousands of decision curves in the literature, right? So show me a decision curve where the confidence interval would help you make a different decision, would give you some information. No one's ever done that yet. Maybe I'll be proving wrong. Go.
Wouldn't you need to have a model in mind when you're choosing the threshold probability in the first place, or how do you usually choose that?
And the threshold model is completely independent of the data. It's completely independent of the model. You can choose a threshold probability even if you have no predictors and no possibility in the model, right? The threshold probability depends on the relative harms of a false positive and a false negative. So if we have no data whatsoever on, say, lymph node dissection in melanoma, and we have no predictors, we can still have a conversation about at what risk of having affected lymph nodes would you remove the lymph nodes in melanoma. We can still have that conversation and come up with the risk threshold.
You don't need to know like the number of false positives you'd be making and so on, just the relative, like the ratio of those things.
Well, no, the number of false positives is data, right? But the threshold probability is nothing to do with the data, it's considerations of harms and benefits, right? And, you know, think about the orthopedic surgery. We're thinking like, well, what risk of dying would you not have the surgery? It kind of depends how much pain you're in, right? If you're in a lot of pain, maybe you take 50 or 60% risk of dying early and still get the surgery. That's got nothing to do with the model. It's got nothing to do with the prevalence of death. It's got nothing to do with the predictors or anything. It's just the consideration of how you're going to make a decision in the real world. Yeah.
Okay, for model building, let's say you have a question that you wanna, recently there's a question about whether we should put race in your prediction model. Can your idea be used to address that kind of question?
Well, let's pretend you didn't say race, because that's like a set of controversial features.
Yeah.
Yeah, so if you're interested, this is actually, this is a kind of cutting edge, was that net benefit was for the evaluation of models, right? And I think the title of my talk is how do you evaluate a model? All the papers are on net benefit for the evaluation of prediction models and so forth. But folks have just started doing research to use net benefit as what you're trying as the objective function, right? So what you're trying to optimize in model selection. And this started actually from marker or predictor selection, because an algorithm I've used, and if anyone else has used this, is you take the predictor with the highest AUC, and then you search over all the other predictors to find the one that adds the most, and then you keep doing that until you're not improving AUC anymore. But you might have a model that's very, very predictive. Sorry, you might have a marker. Marker A is more predictive than marker B, but marker A is expensive and the patient has to come into the hospital and get a biopsy or something, and marker B is age, something you already know. So the idea there is to include test harm, and you only include the marker if it improves net benefit. So the improvement in net benefit is greater than the decrease due to test harm. So that's one thing that's being done. The other thing that's kind of really cutting edge is in all machine learning algorithms, the basic way they work is you create some model and you get some metric, and it's often say mean squared error. And then you perturb the system, and if the mean square error gets better, you perturb it more, and if it is going in the other direction, you do it in the right. And you keep doing this until you reach a maximum of the optimum mean square error, and that's your model. And this, you can actually go into ML algorithms, and you can shovel through the code, and deep in the code, you see the number 0.5. Right, and that's how they're splitting up true positives, positives and negatives. It's based on 0.5. It's just written in the software from the year dot, and that's because the original machine learning was for things like rainfall or Amazon, right? And it's like, well, is it worse to suggest a movie that someone doesn't like, or not suggest? Well, it's not really clear, right? So what some people are doing is saying, well, we've got a mammography, a machine learning algorithm to read mammography. We better tell this machine learning algorithm that it's far worse to miss a cancer than to call something cancer that isn't. And so that's a kind of new area of research. I haven't actually seen many papers, just starting to see a few papers come out on it. And there's one that came out and said net benefit's the best thing since sliced bread, and I don't really believe it, actually. I think the results were totally plausible. But it's actually to say, use that as the objective function to build your model.
All right, I think we
that's